What I'm going to talk about is the work that we've been doing on the Sarsen stones at Stonehenge. And as I'm sure you know, there's been a huge amount of debate, and it's actually over several centuries now, as to whereabouts the stones that were used to construct Stonehenge came from, their transportation methods, the routes that they might have taken, and all those sorts of things. Now, it's worth remembering that Stonehenge is constructed from two sets of stones, and I'm sure you know this, but there are the smaller blue stones, which is a kind of catch-all term for a mixture of igneous and sedimentary rocks, which are known to come from various parts of Wales now. But in comparison, the big Sarsen stones, the ones that make up the main part of the architecture of Stonehenge, have received very, very little attention. I think that's probably because of the fact that there are large areas with big extents of Sarsens, only to 20 miles or so to the north of Stonehenge on the Marlborough Downs. So conventional wisdom almost has always assumed that these stones must be local. So there's been a bit less attention paid to them compared to the more exotic blue stones. In fact, the idea of these Sarsens coming from the Marlborough Downs can be traced back to the late 1500s and the work of the antiquary William Lambard, who was the first to suggest that he called them the grey weathers, of a similar appearance to Stonehenge, occurred on the Marlborough Downs. So we've had this idea kicking around for maybe 400 or more years that the Sarsens come from the Marlborough Downs, but until the work that I'm going to talk about today, nobody had tested that idea systematically, and that's really what we set out to do in our research. And so what I'm going to try to do is I'm going to talk you through very broadly, almost as a timeline, as a bit of a story as to what as to how this research came about and how we conducted it. And I'm going to try to tell you, I suppose, what we can say with confidence from our research, and also what we're less certain about, because you'll have seen last year there was an awful lot of media coverage, and in some cases I think the media went slightly further than I would comfortably with our data. So what I'm going to try to do is, I suppose, tell you, I think, where we are, but also finish up by saying a bit more about what we plan to do in the future. Before I kick off, I'm going to say a little bit by way of thanks. Saves doing it at the end, but obviously the work I'm talking about was funded, so big thanks to the British Academy and to the Leverhulme Trust. Obviously also big thanks to a whole team of co-investigators. So Katie Whitaker is here this evening to help answer questions, but I've also got my colleagues Jake and Georgios Stewart at the University of Brighton, and also archaeologists including Tim Darville and Mike Parker-Pearson. We wouldn't have been able to do our work were it not for English Heritage giving us extensive permissions, and groups of people who helped us with analyses, and then also the various people who let us onto their land to sample Sarsens. That includes people like the Forestry England and the National Trust. So a big thank you to everybody there. Now, before I talk about our work in any detail, I just want to give you a little bit of context, because I'm sure most of you know a fair bit about Stonehenge. You may not know as much about Sarsen stones. So I just want to start with a few slides of context. Now, if you visit Stonehenge today, I'll show this slide from English Heritage. What you see is a complex circular bank and ditch enclosure, so that's the henge, and then in the middle of it are a series of standing stones. The biggest ones of those, as I've said, are the Sarsen stones, but there are also other Sarsens within the bank and ditch enclosure, and I'll just circle those there. So there would have been 4 station stones, which sit in a kind of a rectangle around the main centre of the monument, and then to the north southeast, there's the heel stone and what's called the slaughter stone. And you can see by the way that I've highlighted everything there, hopefully you can see the symmetry of the monument as it aligns with the solstices. I'm not going to say anything about what Stonehenge was for and so on. That's really the realm of archaeologists. I'm a geomorphologist and geologist, but clearly this alignment with the sun must have been a critical part of the function of the monument. Now, if we zoom in a bit and we go into the stone circle itself, you can see the main architecture here. I'm not sure whether my mouse is visible. I hope it is, but you can hopefully see the Sarsen circle around the outside. That has 30 Sarsen uprights, and it's not clear whether it was a complete circle of lintels, but it's likely to have had 30 lintel stones sitting on top of those Sarsen uprights. And then in the middle of the monument is 5 sets of what are called Sarsen trilithons. So these are these sort of door-shaped arrangements with 2 Sarsen uprights and a lintel stone across the top. And the stones in the trilithon horseshoe are absolute monsters, I think it's fair to say. Stone number 56, which is over here, is an estimated 9.1 meters in length, so that's getting on for 30 feet in old money. Stone 54 down here has an above ground weight of around about 30 tons. So these are really, really big. If all the stones were intact and all present, we'd be looking at potentially 80 or 81 Sarsens at the site. That's assuming 81 is assuming that the lintels are complete around the top of the Sarsen circle. There are 52 stones remaining today, so a large number have been removed in prehistory. The stones themselves were moved on site around about 2500 BC. So this is in the second phase of construction of Stonehenge. So people like Tim Darville and colleagues have done some sterling work modelling the radiocarbon ages from Stonehenge and have been able to identify 5 main phases of development. And the first of those is shown in this slide on the left, when the henge itself, the bank and the ditch structure was built, and that's around about 3000 BC. The heel stone was probably already on site or in position at that time, and it's really around about 2500 BC when the Sarsens and the blue stones were moved into their positions. The third phase involves some slight rearrangement of the blue stones, maybe 200 or 300 years later, but by that point the main configuration of the stones was largely as they are today. So that's Sarsens and Stonehenge. As I said, I want to say a little bit more about Sarsens because I suppose there's been a fair bit of misinformation over the years about Sarsen stones, and actually how they form is quite integral to the arguments and the methodology that we've used. So if you don't know, Sarsen is an English vernacular term for a stone that's technically called silkrete. So this is a type of duricrust, and to my knowledge, there's only one place in the UK where you can actually see silkrete outcropping naturally, and that's down a chalk mine in Pinner, where I had the great, I wouldn't describe it as a pleasure because it was absolutely horrific experience of being lowered down on a rope ladder to look at this silkrete down a 15-metre deep hole. I won't be doing that again. But where you more commonly see Sarsens are in the landscape as shown in the images on this slide. So if you draw a line between roughly the Wash and the Bristol Channel and go sort of south and east of that, you'll find Sarsens moderately well distributed across large areas. And generally speaking, they occur as clusters of boulders. That's when they tend to be more prominent, either in valley bottoms, as you can see on the top left-hand slide picture there, or on the flanks of valleys or on plateau surfaces. How they form, and I just want to spend a minute or two talking about this, just to kind of explain the situation. So most of the Sarsens are a particular type of silcrete, known as a groundwater silcrete. And to understand how they develop, you really have to go back even as far as the Cretaceous period, when the chalk was being deposited. So this little cartoon kind of summarises Sarsen formation as it relates to Wiltshire. So in the top left-hand corner, you've got a situation where you've got some of the older Cretaceous rocks, like the Gault clay and the upper greensand, have already been deposited. The chalk has been deposited in nice warm tropical seas. That's the blue sea at the top there. The chalk basically stopped forming round about at the same time, or stopped being deposited at roughly the same time as the Alps were forming further to the south and to the east. And the Alps themselves developed as a result of the African tectonic plate colliding with the European plate, and it caused mass mountain building in parts of Europe. But the ripples of the tectonic pressure caused deformation over the British Isles. So the chalk and the greenstand were folded, and then within those folds, in the London Basin area and the Hampshire Basin, we see the deposition of a series of sediments called the Lambeth Group and the London Clay. These are of Paleogene age. The Paleogene, for those of you who don't know, is basically it's the early part of what used to be called the Tertiary period. So we're looking at probably 60 to 80 million years or so ago. Now these Paleogene sediments are a lot softer than the other rocks. So as time progressed and there was more uplift, so these rocks began to be weathered through. And you can see that on the top right hand cartoon, where what you've got there is a valley cutting its way through London Clay and through the Lambeth Group. And as it's done that, what happens is that the water table lowers, and the water that's passing through the sediments is carrying dissolved silica, and silica is the main constituent of quartz, and quartz is the dominant cement that holds Sarsen stones together. So what would have happened would have been these silica-rich waters percolated down through the surface, hit the water table within bodies of sandy sediment, and then began to cement them to form kind of almost like lenses of hardened silica cemented sand. And those really are what ultimately end up being the Sarsen stones. So as the landscape further eroded, so the Paleogene cover was stripped away, and you see it in places left as a formation called clay with flints. That's basically the weathered remnants of these sediments. Sometimes you see the Paleogene sediments intact, but where you find Sarsens, they now sit either on plateau tops, often in association with clay with flints, or they're making their way down valley sides, or you find them in valley bottoms and in valley fills. So rather than the old idea that these were some kind of soil feature and that formed enormous sheets across the landscape, they probably formed as lenses or pockets in particular locations. But the critical thing is that they're silica cemented sands. Okay, so hopefully that gives a bit of context both about the Sarsens at Stonehenge and also the what Sarsens are, and very broadly how they form. So having given that bit of context, and see how I'm going for time, I think we're okay. Let's move on to what we actually did at the monument. Now it's worth saying to start with that we've tried on a number of occasions to get money to do work at Stonehenge. We actually had 4 goes at trying to secure funding to do this particular work. We tried 3 big grant applications, all of which were unsuccessful, and we decided we'd break the research down into smaller pieces. So we applied to the British Academy for some money and were successful. Now, Our plan originally with the British Academy project was that we were going to analyse the chemistry of the Sarsen stones themselves at Stonehenge, and then compare the results of that with the chemistry of chippings of Sarsen that had been excavated from various digs in and around the monument. Now, in an ideal world, we'd have liked to have been able to sample from Stonehenge, but hopefully, as you can understand, that's not an easy thing to do. We're looking here at a World Heritage Site with some of the highest levels of protection anywhere in the country. So we pressed on with this work, and we went and we analysed the main stones at Stonehenge, and also analysed literally, well, thousands of chippings of Sarsen that had been dug up in 2 excavations by Tim Darville and Mike Parker Pearson. Now, to analyse the stones, we used a device called a portable X-ray fluorescence spectrometer, which sounds very grand. It's a PXRF for short, and it's basically a form of, it's a portable X-ray gun. And you can see my colleague at Brighton there, Jake Chiborowski, on the right, analysing a Sarsen stone. What the device does is it fires an X-ray at the stone, and that X-ray excites the minerals within the stone, and then it sends back effectively a reading of the elemental composition of that stone. And it's a bit of a laborious process because you have to hold the device absolutely steady for 2 minutes. We did 5 readings across each of the 52 stones, so in excess of 250 data points over several periods. Now, the difficulty with working at Stonehenge, while it's an enormous privilege, you can't do it while it's open to the public. So we had to do all of our work either at night or very early in the morning. And I think I had 4 late night stints going through till about 2 in the morning at Stonehenge, which is, I think it's an experience would be the best way to describe it. And we had 1 very early morning shift when English Heritage set us up with a mobile scaffold tower and some burly scaffolders to move it around. And we were able to get up on top of the scaffold and analyse all of the remaining lintel stones. And you get a sense really of the scale of the Sarsens when you see Jake there on the scaffold tower. And I suppose that was, I mean, that was an absolutely amazing thing to be able to do. Now, what we did with the data that we collected, so the PXRF gives you information for a whole range of different chemical elements. And what we then did was we analysed these data statistically to ascertain how variable the chemistry of Stonehenge is. Now, this is the only, I suppose, really complicated graph I'm going to show, but I'll try and talk you through it relatively gently. So we used 2 main statistical methods. We used one that's called linear discriminant analysis. This is very much a kind of an exploratory statistical approach. So it's not necessarily a sort of a high-powered statistical method, but we applied linear discriminant analysis to our data set. And what it showed initially was that our data points cluster. And hopefully you can see here the clustering. The black ellipse here represents what's called in statistics the 95% confidence interval. So this is a measure of the strength of the cluster almost. And what we identified was that most stones, all of the analyses fell within this cluster. You can see some analyses outside, but for a stone to be classified as different to that cluster, we wanted all of the analyses to fall beyond that ellipse. So a number of these, you can see analyses falling down here. The rest of the data points fall within the ellipse. So we can't really say that these analyses are from a stone that's different. But what we did pick up were 3 stones that were chemically different to the rest of the monument. So these are stone number 26, which is one of the uprights, and then lintel stones number 156 and 160. Now, having done that, we then applied a more powerful statistical test. So what we knew effectively was we had a common chemistry and that suggested that we were likely to have a common source area for most of the stones. So we used a more powerful method, which is called Bayesian principal components analysis. And I say it's more powerful. What this does is whereas in linear discriminant analysis, what you do is you put the analyses into groups according to which stone they came from. With this PCA technique, you don't group things, you just simply let the statistical analysis take each data point in turn. And what this showed was an even tighter clustering. And I think slightly surprisingly, what we found was that actually this stone number 156 wasn't actually that different to the rest of the stones. You can see with this more powerful, we call it an unsupervised method, the data points fall within the same ellipse. But we were picking out again that stone 26 and stone 160 were different. Now, the other thing I'd draw your attention to on these plots are the little red triangles, which are from stone 58. And I'll say a bit more about that in a moment. But the thing to notice here is that stone 58, the analyses sit right in the middle of those ellipses, so suggesting that the chemistry of stone number 58 is very representative of the chemistry of the monument as a whole. Okay. So moving on with our story, we'd finished our PXRF data collection, and we were in the process of analysing the data when I received an unexpected email from English Heritage that very much changed the course of the research. And I can't remember the exact wording, but the email went along the lines of, "I understand that you're doing work at Stonehenge on the Sarsens. Could you give me a ring, please?" And my immediate reaction was, "Oh my God, what have we done wrong?" But it turned out that it was actually good news rather than a problem, in that it was explained that English Heritage had received an email from the United States saying that an elderly gentleman had a core that had been drilled from one of the Sarsen stones and asking, would we like it back? And also asking, would it be worth bringing back to the UK, and would it be useful for our research? And I almost, bit the hand off, because what this really was an actual direct sample from a Sarsen stone at Stonehenge. But more importantly, we knew exactly which stone it had come from, and almost exactly whereabouts in the Sarsen it had been extracted. So I was asked to write a very short scientific case for bringing the core back to the UK, and it arrived back in May 2018 and was held at the English Heritage Stores just outside Bath. Now, this core has a really interesting and quite colourful history. And it dates back to 1958. Now, what you've got to remember is that what you see at Stonehenge today is not only the product of wear and tear over time, but it's also a product of conservation efforts to make the site safe, but also to improve interpretation for visitors. And in 1958, the decision was made by what was then the Ministry of Works, that we needed to re-erect one of the trilithons in the middle of Stonehenge that had fallen over in 1797. And this was the trilithon consisting of stone 57, stone 58, and its lintel on top. Now, they did various bits of prep work prior to raising the stone, and during the course of this, it was identified that there was a longitudinal crack running the length of the stone, and there was big concern that if they raised the stone and then put the lintel back on top, it could collapse. So rather than risk that, a decision was made to pin the stone together, a bit like you'd pin the wall on a house if the wall was bulging outwards. So the stone was raised, and then 3 horizontal holes were bored through the stone, cores came out of those holes, and then they inserted metal rods through the holes, put bolts on the end of them, and then capped the ends with Sarsen stone so that you couldn't really see the gap. And then the lintel stone was put on top. Now, the drilling work was carried out by a company from Basingstoke called Van Mops, and a representative of the company was on site, and it's this gentleman on the left here, a man called Robert Phillips in the nice welly and suit combo. And when the works were completed, he was entrusted with one of the cores to take away on behalf of the company. I suppose it's almost like a thank you. Now, today we'd keep that as an artifact, but I guess, yeah, we're in different times in the 1950s. So Phillips took the core with him on behalf of Van Mops, and it hung in his office in Basingstoke until 1976, when he retired, and it was hanging with a very nice watercolour that Van Mops had commissioned, showing the works. I assume that the company were very proud of their involvement in the conservation effort. But when Phillips retired, he was given permission by Van Mops to take the painting and the core with him. So he retired, he moved to the United States, and he actually moved around 4 different locations in the States before ending up in Florida. And in his very late 80s, he basically asked his son to get in touch with English Heritage to ask, well, would they like this core back? And I've never spoken to Mr. Phillips, and sadly he died this time last year. But it feels to me as if it's almost like an old man tidying up his business. But his sons did indeed get in touch, and the rest, as I say, is history. So the core was returned to English Heritage, and the image on the top left there shows 2 of Mr. Phillips's sons with Heather Sabir from English Heritage and handing over the core. And you can see other images of the core in the bottom there. Now we were given permission to analyse it, which was a phenomenal privilege. And you can see on the top right, that's my colleague Jake again, looking at it with portable X-ray fluorescence. I'm there in the bottom right-hand corner, trying to look intelligent with a hand lens and some very attractive black rubber gloves. But we were able to do some very basic analyses of the core in the English Heritage stores. Now, what we find from that, and I'll just show a couple of graphics here, what we really find from that is just how homogeneous this material is. So the Sarsen stone is incredibly uniform along the full 1.1 metre length of the core. It's very homogeneous both in terms of its grain size, so the sand grains that actually make up the Sarsen, and also many aspects of its chemistry. So the graphic on the left-hand side here shows what's called a sedimentary log, and all it is really is a graph that shows grain size. So what you can see here, you draw a line according to whereabouts the grain size is at a particular depth or length along the core. So much of the core straddles the boundary between medium and fine sand size. There are some areas where there's slightly coarser sand present, but pretty much it's a very uniform material. It's also chemically very, very uniform, as I say. So you can see here, this is just showing the results of the PXRF data. You can see that, these are values for just some selected elements. So zirconium, hardly any variability along the whole length of the core. Silica, the same. The only element that really shows much variation is iron, and that's linked into various amounts of staining that are present on the core. So there's patches and bands on the core where there is a degree of iron staining. That's likely introduced where iron-rich solutions washed through the Sarsen whilst it was still buried underground. The core itself is broken into 6 bits, so it's not an intact tube of rock, it's in 6 pieces. And we were given permission to sample one of these, the smallest bit, and conveniently the core itself, it was in 6 pieces, but each piece was numbered. It had a number at either end marked in permanent marker, so you could match the pieces together. And what we could see was that when we refitted them, we had a completely intact core, even with dead lichen at either end of it, where the drill had drilled right the way through the stone. So we knew we had a record going right the way through this this particular sarsen. Now, I suppose what we did next now really starts to build into the way in which we were able to figure out the source of stone 58, where this sarsen core came from. I should say we always refer to this core as the Phillips core, really very much in memory of Mr. Phillips. So what did we do in terms of analysis? Now I'll be reasonably brief here. That's the picture in the top left here is the actual piece of core that we were able to analyse. So it's about 67 millimetres long. I think the thing that struck me about it really was just how pale it is. So the core as a whole is a creamy white colour, and you can see some of the iron staining here, but the overall whole core looks incredibly pale, and it really struck me that you know, this is the stone that Stonehenge is constructed from. All of the sarsens at Stonehenge would have been dressed, they would have been tidied up before they were put into position. And it must have looked absolutely amazing. I mean, it looks impressive today, but it's very grey. Imagine going to Stonehenge and seeing this gleaming, creamy white structure surrounded probably by a chalk or maybe a grassed embankment. It would have been incredibly powerful. But what we were able to do with this piece was get a whole series of different analyses from it. So we realised that we had a very sort of precious bit of stone here, and we were really careful that we got the most out of it as we possibly could. It's probably, you know, it's a very well travelled piece of stone, this as well. So what we did was, first of all, the whole piece of the core, this sort of 7 centimetre long bit, was transported to Bristol University, where it was cut in half lengthways. English Heritage kept half, and we were then given the other half to dissect further. So we did that at the Open University in Milton Keynes. So the core went back to Brighton, then it went on a road trip to Milton Keynes, where it was cut into 3 pieces. And then each of those pieces were then cut in 2, so cut the tops off, and then those tops were also cut in 2. And we were able to use the lower part of these pieces to make microscopic thin sections from. So you can see all the bits that we used here. And then down at the bottom, we use 3 pieces to get detailed chemical analyses. And we also used 2 smaller pieces for isotope analyses. Now, what I'm going to show you is not the whole data set. I'm just going to show you some of the thin section evidence, and mainly focusing on the chemistry, because that's the bit that's most relevant for the story today. The other thing that we did was we had the core analysed at British Geological Survey. Before it was cut into pieces, it was taken to British Geological Survey just south of Nottingham, where it was put through a CAT scanner, so a CT scanner, rather like you see used for brain scans, so that we could look and see what the internal structure was like. Now, what this little animation is doing is it's giving you effectively a cross section through this core in 30 micron slices. And what you can hopefully see is it's not very exciting, I think is probably the fair thing to say. So there's very little in the way of structure within there. The stone is very homogeneous. There's no bedding or anything that you might expect to see in a sedimentary rock, and in fact it's really quite dull. But that's good, and I quite like this bit where the core rotates, but you can see there just the real lack of structure or any grains or any banding or bedding that might be present. The reason it's good for us is because it means that the rock again is very homogeneous, meaning that its chemistry is likely to be homogeneous. I might cut through this before it runs all the way through, because it, looking at a rock that's really quite dull isn't that exciting. But at least what we're able to tell was that there were no sedimentary structures, and what we were dealing with was something that was very, very uniform. Now, we see the same thing when we look at it in thin section. So if you've never looked at a rock under the microscope, you can do it in two main ways. You can look at it under what's called plane polarized light. So that's a bit like normal white light. That's what's shown at the top here. Or you can look at it under what's called cross polarized light. And what that lets you do is see the different minerals that are present. And that's the bottom two images. And the scale bars there give you a sense of the detail that we're looking at. But what we can see from this, again, is it bears out the idea that this is a very, very homogeneous material. It's basically quartz sand grains cemented together by quartz. And you can see that in the bottom right here, where you can even see some of the original grains, actually. That little line, hopefully you can see in that particular part of the thin section, is what's often referred to as a dust line, and it separates what was the original grain from its cement. So what these are it's a quartz sand, or a very, very quartz-rich sand, that's been cemented together by more quartz, and all of the crystals are very tightly interlocking to give it additional strength. The image in the bottom left just gives a sense of, at a bigger scale, of just how homogeneous it is. It looks a bit like a kitchen worktop there, doesn't it? But I suppose the message out of this is that the stone is very, very uniform. So we're getting a sense that the grains on the core are uniform, the chemistry of the core is uniform, and the actual rock itself, when you look at it in detail, is also very uniform. We applied a number of other techniques to look in a bit more detail at the chemistry, and I'm building up to the story of where the chemistry comes in now, really. So we use one technique, which is a technique called QuemScan. And what this does is it takes your thin section and it scans it in incredibly high detail, and it tells you what the different minerals are that are present. So perhaps unsurprisingly, we found that the samples were 99.5% quartz. So the quartz on that slide is all shaded in yellow. But what we also picked out were very small proportions, so this is the 0.5% remaining, of non-quartz, we call them detrital minerals. These are other grains that would have been present within the sand. And it's these grains that are really, really critical to our work trying to figure out whereabouts the Sarsens came from. What we did with the, so we also did some chemical analysis. So we crushed up some of the smaller samples, and then we analysed them using a technique called ICP-MS. We didn't look at all of the data. So ICP-MS gives you data for around about 60 different chemical elements. We focused in on a subset of 21 elements. Because we wanted to be very careful that we were only using chemical elements that were immobile. And by immobile, I mean were unlikely to have moved around or have been dissolved out or washed in as a result of weathering. So you've got to bear in mind that these Sarsens have, many of them will have sat either underground or on the surface for, potentially hundreds of thousands or millions of years. Stonehenge itself has been stuck up in the atmosphere for 5,000 years. So there's possibilities for weathering. So we had to be very, very careful that we chose only trace elements that weren't likely to have been mobilized. So we didn't focus on things like iron and calcium, which are very mobile in near surface environments. We used a suite of very stable elements. Now, briefly, to explain what we did, we wanted to create what we'd like to think of as a chemical fingerprint from stone number 58, and then to be able to compare that with the chemistry of Sarsens from various sites around the country. But a big issue with doing that is that different Sarsen stones contain different proportions of quartz cement. So some, like our one, are very, very well cemented. Others are a bit more crumbly and are a bit less well cemented. And the problem is that the amount of silica, the amount of quartz cement, affects the chemical data that you can get when you analyse the stone. And if I try to explain this with these two little cartoons on the right-hand side. Now, what these are trying to show is effectively a sand, and it's made up of quartz grains. Those are the big sort of oval-shaped ones, and then various other minerals. And if we then cement that with silica or with quartz, as shown here, you can see that you get a very different effect if you've got a large amount of quartz cement, where it's all very, very densely cemented, compared with a less well cemented situation. And if you plotted the data from this, what you would find would be, in this case, because you've got a bit less silica, because what we're doing, we're measuring chemical concentrations in parts per million. So obviously, the more quartz there is, proportionally, the less other things there are. So in this case, if you look at the graphics, the red line here would be illustrative of the situation with the top diagram here, where we've got a Sarsen with a bit less quartz cement. So relatively, we seem to have a bit more of the other elements. Down at the bottom, we've got a much more quartz, so much relatively less of the other elements. But actually, they're exactly the same chemical composition in terms of the original host sands, which is really what we're interested in. And if you compared these two graphs, you'd say, well, they're not the same stone, but actually the sands are the same. And that's really, it's the sands rather than the rock as a whole that we're particularly interested in. So what we do is we, rather than just simply looking at the raw data, which is affected by what's this process that I've called silica doping, what we do instead is we normalize the data. So, and that sounds very grand, but all that involves is taking the data for each of our immobile trace elements and dividing it through by one other immobile trace element. In this case, we choose one called zirconium, which is incredibly mobile. And what this does is it cancels out that silica doping effect. And it allows us to compare Stonehenge with Sarsen stones in other parts of the country. Technical bits aside then. So what we have data from the Phillips core. We've got our 3 samples, and we divide the data through by zirconium, and we end up with a plot that looks rather like this. And what this shows is there's a little bit of variability between the analyses in elements like, well, one slight difference in rubidium, for example, but actually, and you have to trust me on this, from a chemical perspective, that's an incredibly uniform rock. The elements are varying very, very consistently with one another. So what we do is to create what we think of as our chemical fingerprint. All a chemical fingerprint is a graph of chemical data. But what we do is we take the median value, and then we add a small degree of instrumental error. So it's worth noting that all, even high precision instruments, have a degree of error associated with them. The beauty is that we know what that error is, because we're given data that allows us to calculate that when we get the analyses conducted. So we can add error bars onto our median values that give us a sense of the potential variability. So what you can say basically is that the chemistry of this stone is actually, it's not a line, it's a zone between the maximum and the minimum errors. So you'd almost think of that as being, rather than a line, it's almost like an envelope of chemical variability. So we had, as a result of this process, and by being able to access the core, we had a geochemical fingerprint for Stonehenge. Now the next part of the story really relates in comparing that chemistry against Sarsens from across southern Britain. So I've shown this map in a variant earlier on, but what we did, so you can see that Sarsens occur in a large number of areas. what we wanted to do was we wanted to really sample areas that have decent clusters of stones. So rather than say individual stones, focus on areas where we can be confident that they're likely to be either in situ or they haven't been moved very much. And within our budget, we couldn't sample absolutely everywhere. So we focused in on the sites that you can see here. But we sampled sites everywhere from Devon up to Norfolk. We didn't include places like the Chilterns because these are areas where most commonly you find a material called pudding stone. And pudding stone is basically a sarsen that's got lots of flint pebbles in it. And we don't find pudding stone at Stonehenge, so we didn't think it was worthwhile sampling within the Chilterns. But we did sample 6 of the main areas of sarsens within the Marlborough Downs area, and those are shown on the inset map here. So we went up to Monkton Down and Totterdown Wood up on the top of the Downs, and then we also signed West Woods to the south of the River Kennet, and then we also sampled 3 of the big, they're called Sarsen trains, Sarsen valley bottom accumulations, north and south of the Kennet. And for each of those sites, we sampled 3 stones and we analysed them. And I say, you might think, well, 3 stones doesn't sound like very many, but that's based on work that, I mean, I've done most of my research in on Silkrete in Botswana, and we've done a lot of work trying to figure out how many samples do you need to characterise an area, and 3 is usually perfectly adequate when you're dealing with a very homogeneous material like this. But what we did with the data, so we've got all of the analyses, all of this, the same data, we treated them in exactly the same way. So we produced geochemical fingerprints for each of our sites. We worked out the instrumental error. And then what we could do was compare our data with the data from the Phillips core. And the results of that are shown in on this slide. Now, this is going to look very, very small, but don't panic, because I'm going to put an enlarged version of the data on the next slide. But what it hopefully illustrates is how we made our comparisons. So on each of these little graphics for each of the sites, there's a black line. So that's the black line for Stonehenge with its error bars. And then the pink bands here are showing the effectively the error bars, the upper and the lower error bars for each of our sites. And in order for there to be a direct match between the Stonehenge core samples and a source area, potential source area, then you need every single element to overlap with the pink zone within the limits of instrumental error. So you don't necessarily need to get the line overlapping with the pink zone, but you do need all of the elements to have at least their error bars overlapping with the pink zone for it to be considered a permissible match. And hopefully what you can see here is that there's many of these sites that are nothing like it. So we could actually go around and we could knock out a number of locations where we could say definitely not Devon, definitely not Dorset, definitely not Kent, definitely not parts of Essex, and so on and so forth. And if you look and zoom in into the examples from the Marlborough Downs here, this hopefully is a bit bigger for you. You can see that it's definitely not Monkton Down or Totterdown Wood, so the sarsens that were on the north side of the plateau surface, on the other side of the Kennet. It's not Clatford Bottom, it's not Pickledene, it's not Lockridge Dean. The only site where we get a permissible match was West Woods in Wiltshire. Now you might be looking at this thinking, hang on a minute, that doesn't match for uranium. And you're absolutely right that the black line doesn't overlap, but the error bars do. And what that means is effectively you can't say statistically or chemically that those stones are different to one another. The fact that the error bars overlap means that within the limits of instrumental error, then these materials are the same chemically. And on that basis, this is really where we've drawn our inference that from this one site having a direct match, we can say that the stone 58 was likely sourced from westwards. And then by inference, if you think back to the statistical data I showed earlier on, where I said that stone 58 was representative of 50 of the 52 Sarsens left at Stonehenge, we can say that that the majority of the stones at Stonehenge likely came from westwards. Now, note here, I'm not saying we can pinpoint exactly where in westwards they come from. I think what we have here is we have an area, but at least what it does is it gives us the basis for further work that we can do to pinpoint that in a bit more detail. Now, I'm just going to finish up by a short section, really, saying, well, you know, what's so special about westwards? Now, Katie will be horrified by this, so cover your ears now, please, Katie. So Katie's doing her PhD research in westwards, and I'm sure thinks it's the most exciting Sarsen area in the world. Actually, the Sarsens in westwards really aren't that different to the Sarsens that you find in other parts of the Marlborough Downs. And my gut feeling is that this may well have been a very pragmatic choice to source stones from this particular area. So westwards is south of the River Kennet. It has the beauty that it's up on a plateau surface. So you've already got a bit of elevation, maybe, if you're wanting to move large stones over long distances. You don't have to drag them up from the valley of the Kennet, because most of them are already relatively high up on a plateau surface. But other than that, the stones themselves aren't really that spectacular. What we do know is that stones occur sporadically throughout the woodland. Some of the biggest clusters are in a couple of valleys that join within the woods. So they're a bit like the Sarsen trains that I was mentioning earlier on. We also know, the other thing that we do know is that clearly this was an area that was very, I don't know about, I'd say well populated, but it was certainly a centre for early Neolithic activity. So it's not that far from Avebury. It's also not that far from several other important Neolithic sites like Knapp Hill. And there have been archaeological surveys of the woods, in addition to the work that Katie's doing at the moment, that have identified, for example, a very impressive, there's a 40-metre long chambered early Neolithic long barrow down here. There's a Sarsen standing stone in the southeastern part of the woods. There's several stones that are suspected to be Sarsen polissoirs, which are stones that were used for polishing axes. I think more interestingly, though, is that there's been LiDAR investigations. So these are remote sensing investigations that have revealed prehistoric field boundary patterns in westwards. And there's a very good chance that during the early Neolithic, this area wasn't wooded. And it wouldn't surprise me if the area that's now westwards didn't look that dissimilar to other parts of the Marlborough Downs where Sarsens are much more visible. So it might just be a case that people haven't really looked in this area as a source potentially for Stonehenge, because, and if you excuse the pun, they couldn't see the stones for the trees. But we do know that it is an area that had large numbers of Sarsens. Now, there's a complication in this, which is that many of the Sarsens that were in westwards have been broken up during the late 19th century and early 20th century and used as things like road aggregate. So actually, many of the Sarsen stones that were in westwards are now under the A4, where they've been used as road base. But we do know from maps from even as recent as 1924 that there was at least one big Sarsen train within westwards. And now you can see them if you wander through the woods. You'll see Sarsens all over the place, but you do also see the signs of these 19th and early 20th century workings. And in the bottom corner here is a photograph from Katie showing the concrete base of a stone crushing machine. Yes, there's lots of opportunities to do more work in Westwoods, but we are slightly hindered by the fact that many of the Sarsens, in fact probably the majority of the Sarsens, have been removed. But that's I think that's really, and I've spoken for about 10 minutes longer than I told David I was going to do. But that's really where I wanted to get to in terms of our story of what we've been doing at Stonehenge and how it is that we've come to identify Westwoods as a likely area from which the Sarsens originated. I'll just wrap up. I see David switched his camera on because he was getting excited then. I'll just wrap up with the sort of the so what's next. What are we doing now? Oh, he's gone again. What are we doing now? I think there's an awful lot that we can still do, and I think what we've done really is we've sort of it's the tip of the iceberg in a sense. So at the moment we're doing a lot of work, really analysing to death the Phillips core. So we've conducted a whole series of other analyses on the samples from the core, and we are in the process of publishing a paper on that. Now that's been through the first review. And it should, if it gets accepted, be out probably March time, I would think. The second thing I'm really keen to do, if we can get the money, is to refine the I've called it here the Westwoods geochemical signature. So at the moment, all we've got are analyses from 3 stones from Westwoods. And we don't know how wide an area that particular distinctive chemical signature spreads over. So I'm really keen that we can try to sample more and really try to pin down the potential Sarsen sources a bit more tightly. I think there's also the possibility of starting to think about whereabouts were the Sarsens extracted from within Westwoods. Now, in order to do that, we need to be able to identify Neolithic extraction pits, and that's not so easy in a landscape where there's been very extensive 19th century Sarsen removal. But we're talking at the moment about possible ways that we can tell, a 100-year-old Sarsen pit from a Neolithic Sarsen pit. And I think the other thing that's got real potential is we may even start to be able to figure out the routes that the stones were taken to Stonehenge. And the thing that's hindered efforts in the past has been the fact that we didn't know the start point of the journey. Well, now we've got a reasonable idea of the likely starting area. We can start to think about routes. So on this little map, I've shown the route proposed by Hill. I think it's in the 1960s, who thought that the Sarsens were transported down the Avon Valley. In our paper last year, we proposed, this is really Mike Parker Pearson's preference, was a route that went slightly further west. But potentially, if we can find fragments of Sarsen from archaeological sites along any of these routes, and we can see if they match with Stonehenge, we've really started to be able to pin down the possible pathways. But I think that's a few years into the future before we'll be able to attempt anything like that. I think the first thing really is refining this signature. So that's really what I want to say. Final slide is just to be completely shameless, because I am. You might have seen just before Christmas, I'm sure many of you read Current Archaeology. If you don't, it's a cracking magazine. But every year Current Archaeology do a series of awards, and we were absolutely chuffed to bits to be nominated as one of 6 projects of the year by Current Archaeology last year. And as I say, I'll be shameless. It's a public vote that decides who wins the awards, and all you've got to do is go on to www.archaeology.co.uk/vote and obviously put your vote in for Stonehenge. Okay, I'll leave it at that and say thanks very much, and welcome. Very happy to answer any questions you might have. And apologies, David, for talking for longer than I said.
Well, that's fantastic. You will have noticed I hadn't fallen asleep because I had the full start just to prove I was staying awake. Absolutely fascinating talk. So thank you very much for that. So we've got the batch of questions already, and we'll start off with the first one from Dennis, which is, where are these Sarsens in Westwoods? Now, he asked that question before you actually started talking, and in between times we've had Simon Banton has sent through a URL, which, if I can ask if you can drop your stop sharing the wonderful photo of Stonehenge, then Simon's put together. Excellent. He's put together one of his amazing maps, which is.
Oh, I'm looking forward to this. Goodness.
Sorry, what are you? Oh yeah, yeah. So this is his map. It's web.org.uk/Westwoods, and you can zoom in. You know, it's a standard map, and you can click and you can see all sorts of detail, so you can really find your way around. Mm. So that's fabulous, and Simon might put that URL in the chat for everyone if he's feeling enthusiastic.
But it's worth saying, if anybody wants to go and have a look, driving from the north, and there's a car park in the north edge of Westwoods, and even if you walk 10 minutes down one of the Forestry Commission paths, you'll see some monster Sarsen stones just off the path. Katie can say a lot more about that because she's pounded Westwoods.
Hello.
Haven't you, Katie?
Yes, I have.
Hi, Katie.
I have. Hello, folks. Yeah, I'll just briefly say something about the Sarsens in Westwoods and the locations. They are scattered about the woods. Obviously, Simon's map uses data from the fieldwork that Lynn Amadio and the Wiltshire Archaeology Field Group did over a 5-year period working in Westwoods. So that will show you some of the features from their report. Their report is on the Archaeology Data Service as well. So you can take the text of the report and Simon's map and have a look around Westwoods. But yeah, there are 3 car parks that provide you with access to Westwoods. If you want to look at Sarsen stones, you should either use the main car park on the east side of the woods or the north car park and walk in. It's best to go in the autumn or winter this time of year, because otherwise most of the areas with the stones are really overgrown. So if you actually want to see the stones, now is the time to go, albeit bearing in mind our current restrictions, your own health and safety. You know, don't fall over and break an ankle and have to call out the air ambulance now. It's not a good time for that to happen. I'm sure you're all really sensible and know what you're doing though. And yeah, you need to be looking in the area of Stony Copse and the valley in the middle of Westwoods called Hursley Bottom. If you want to be able to see Sarsens in the wild in Westwoods.
Thing to bear in mind, these are all Stonehenge rejects. I don't like to say that, but you know, these are obviously not the ones, but they give you a sense of the scale of some of these stones.
And just to add that Katie was suggesting she might be able to arrange a walk for us into the woods when everything, sort of the restrictions are off and when we can actually see something.
Yeah,
which would be fabulous. Can't wait. Okay, next question. This is from Steve. Quite a long one. So told that Sarsens, the Stonehenge Sarsens have identical chemistry. The exceptions are 26, stones 26 and 160.
That's right, yeah.
But there's various different colours. Do those sort of represent different chemical compositions?
Yes, so in short, yes, there are stones at Stonehenge that have slightly different colours to them. So I think that was picked up in the laser scanning survey that was done. I think it was 2012, was it? The Abbott paper. And they picked up slight differences in colour on some of the stones. Now, that included, I think the main thing I remember was some slightly more orange coloured ones, which are likely the product of, what you've got to remember is that these stones would have been sitting underground. So when they were formed, they obviously formed underground, but then even when they've been eroded out of the rock, they would probably still be sitting in the subsurface. And if they're in clay with flints, that's got an awful lot of iron within it. So it's not a surprise that some of them have got a bit more staining. And I guess some of those stones, the staining just hasn't been removed by the dressing process. Now, it doesn't make any difference at all to our results because we weren't looking at iron. We deliberately picked chemical elements that, as I said, weren't going to be mobilized in the natural environment. So that's why we can say the stones are homogeneous, because the sands are homogeneous. I suppose that's the point. It's not necessarily the whole sarsen, it's the sand grains that are within the sarsen is what we're analysing. And that's what's chemically consistent, even if there's sort of superficial staining and so on in some of the other stones.
Yeah, okay, thanks. And Dennis and Anne, I think someone else, have asked whether the Avebury stones are from the same source.
Oh, that's a big question, and that's something else that would be. I mean, I didn't say that in the things to do, but that's another enormous project that you could potentially do. Looking at you could start it by looking at the PXRF data to see if there's similarities just using this non-destructive technique. I don't know whether there's any pieces of Avebury anywhere that we know come from a particular stone that we may be able to analyse the chemistry of. If there are, well, that would be absolutely fantastic. Yeah, I mean, I think it's really interesting that because what you might be able to start to think about then is, were Neolithic peoples using the same sources? I suppose the interesting question is, why do people use West Woods? Was there something special about West Woods? Was it pragmatic, as I wonder? Was Avebury from the same area? I mean, some of the stones at Avebury, the stones at Avebury aren't dressed. And some of them are, correct me if I'm wrong, Katie, some of them are bigger, aren't they? They're certainly wider.
Oh, yes. Yeah.
And weight-wise, some of them are much bigger than the stones at Stonehenge. Could be the same areas, but again, I think rather like going back to sort of, William Lambard's ideas, it's guesswork at the moment until we do some real proper analysis of them.
So that's your next project.
I'd love to do it. I mean,
keep it quiet for a while.
It certainly would. The problem with Avebury is there's an awful lot more stones there than there are at Stonehenge. I suppose the plus side is you're not restricted in terms of getting in there and having to go in there at night. So, yeah.
Okay, and Heather, and I'm sure someone else asked, you mentioned there were 3 stones that weren't the same chemistry.
Yeah.
Any ideas where those are from?
No, so we've got 2 main ones that are different. So the first statistical analysis suggested that there might be 3, but actually when we use the more powerful technique, there's 2. The problem with that, it would be lovely to know, but that's another thing you could start trying to find out is if the chemistry of those stone matches. The only problem is that you would need, in order to be able to compare those stones to our samples from across the country, you'd need a piece of them. And that would require permission to drill a hole or 2 into Stonehenge. And I can see Katie smiling at the bottom there. Having found out what we've found out so far, you never know. I think we've demonstrated the value of actually having a piece of but I guess that core was drilled for other purposes. I think it might be a very different story asking to deliberately drill a hole into probably the most famous Neolithic monument in the world. I'm not sure I'd want to ask, but yeah. At the moment, we just don't know. We don't know.
Yeah. Okay. I myself can answer a question that Sarah has just asked, but that follows up with one that Simon has asked, which is that about other sources of sarsen that are closer to Stonehenge itself, because there are other sarsen stones in the landscape, like the Cuckoo Stone, the Bulford Stone, and a couple of long barrows. Have you plans? Would you like to PXRF those?
So this is a really good question, and we were asked this a lot after the paper had been published. We were asked the question, why did you not sample nearer to Stonehenge? And I think I've got, well, one very good reason for that is that I don't think it's reliable sampling isolated stones, because we just don't know if they've moved. So I wouldn't want to take a piece off the Cuckoo stone or the Bulford stone or any of those stones. But given they're isolated boulders, and given we suspect that, Stonehenge Sarsen's been moved quite a long way, some of these stones could have been moved around in the landscape. Now there are, and Katie probably knows more about this than me, I think it's near Lark Hill, isn't there? There's quite a bit of Sarsen debris around there. You could possibly sample some of that. I guess my bigger question is, and if I was being controversial here, I really don't know that there were big areas of Sarsens in the vicinity of Stonehenge. And the reason I say that is because if there were, one argument has been, were there lots of Sarsens near the site and they were all used to make the monument? Now, if that was the case, I would expect that you would see an awful lot more Sarsen debris. You'd probably see a lot of other Sarsen stones left behind that weren't big enough. Or you'd see lots of vernacular architecture in that area containing loads of Sarsens, like you do further north. And Katie can correct me on this, but it's not really there to the scale that you might expect if you had you'd need a really big area of Sarsens to get 80 monster stones and then also have leftovers, because you wouldn't just have 80 monster stones, you'd also have lots of smaller ones and other size ranges from these original lenses. So I genuinely don't know whether there were lots of Sarsens in the vicinity of Stonehenge, but I doubt it. We can test that, because we can look at the chemistry of Lark Hill, for example, and see, has that got the same chemistry as West Woods? Because it would have to have if we're arguing stones were local.
There probably were some more Sarsens in the area than we see now. Just as there were many more Sarsen stones in North Wiltshire, where we're familiar with seeing them around the Kennet Valley, but obviously so many, tens of thousands, have been removed from that landscape as well over the years. So there probably were more further south in the county on Salisbury Plain, just as there are a few that are visible now. But in terms of survivals, there are probably more surviving, but for example, in the earthwork lynchets of prehistoric field systems and that are still, where they've not been destroyed on Salisbury Plain. So there are probably a few more there, but it really does look like the numbers were never as great as further north in the Marlborough Downs. Or comparatively, if you go south down to Dorset, or if you go over across onto the Chilterns, again there were tens of thousands of those types of Chiltern Sarsens, and Silcretes overall, the pudding stone and the Sarsen, most of which have been broken up by the post-medieval industry that's used them all. So it is a really difficult question to answer. I've made a few inroads into trying to sort of kind of get my head around that idea a little bit with using archive mapping and so on, but it's a really tricky.
I mean, the other thing that's worth saying is that what you would expect if there were large areas of Sarsens, nearly always big areas of Sarsens occur with big areas of clay with flints in the landscape, because of the fact that they're associated with this sort of weathering process and these old sand deposits. And if you look at the geological map today, out on Salisbury Plain, there aren't that many patches of clay with flints. So, okay, they could have all been eroded, but you'd still expect to see some more in the landscape. But I say, that's the question, is does that geochemical signature of Westwoods extend a bit further south towards Salisbury Plain? I personally doubt it, but it's very testable.
Simon's just added that you can dig his garden in Fildene, where he's got little bits of Sarsen under the turf.
Yeah.
Moving on, Natasha and I think it was Suzanne asked where the actual 3 stones you were that were analysed in Westwoods. Were they sort of together? Were they spread out? again, what do you think there might be variability within the
Yeah.
Westwoods scatter in inverted
Yeah,
commas?
so we actually sampled in 2 areas, and 2 were relatively close together, the samples, and 1 was further away, but they're probably separated by half a mile, something like that, weren't they? I would have thought.
Yeah, hardly even that, perhaps.
Yeah, so we've got a signature from a reasonably specific part of Westwoods. And it's the same with the other areas. I mean, when we sampled Clatford, for example, that was many, many years ago. We sampled in a reasonably restricted area. Yeah, so that's the thing. I think that's my point about wanting to know how big an area this signature covers. And I think the things we can say fairly confidently is it can't go much further west, because if it goes much further west, it starts to impinge on where the Sarsens that now are at Lockridge Dean originated from, because they've all rafted down from the hilltops into the valley bottom from what would have been Sarsens higher up. And it can't extend very much further north, because that's impinging into the Clatford Sarsens and the ones that form Piggledene and the ones that have come off the plateau surfaces to the north. So it could go a little bit further east, but geologically then you're getting into Paleogene sediments, London clays and so on. So I don't think it can't cover that big an area, but it's something again that I'd really like to find out a bit more. Is this whereabouts within Westwoods is this signature?
So, and then Catherine, and I think Sarah, and maybe Suzanne, asked what happened to the other 2 cores. You said there were 3.
Now that's a good question. Now, can I share my screen again?
Yep.
Because I was thinking about that one earlier today. Let me see if I can do that. So if I just share that now, quite amusingly, not that long after the announcement was made that this core had arrived back in the UK from America, another one was found in the museum at Salisbury. So we've been saying for ages we don't know where on earth these cores have gone, and one of them, or at least a part of one of them, had been sitting in a box in the museum store in Salisbury. We don't know since when, because it's given an acquisition number that suggests it arrived, or at least it was catalogued in about 2010, I think it is. But it's a piece of one of the other cores, so it's not a whole core. It's a section that's, where are we looking at? We're looking at maybe about 20 centimetres long, and we can't match it up with the other core, but we do know it's probably from the middle of the stone. There's no lichen at either end of it. But unfortunately with that one, we haven't been able to analyse it. But there must be other bits of core kicking around somewhere, and the third one must be around. And it would be lovely to be able to get more analyses, because actually what we'd then be able to know is how homogeneous really is stone number 58. We think it's pretty homogeneous, but it'd be lovely to be able to demonstrate that.
I think we'd better think about letting you go, but because there's still a whole bunch of questions. But
well, I don't mind. I'm happy to answer a couple more. Don't mind.
Not nipping off to the pub.
No, I don't think anybody is, are they? No.
I don't think any of us are. Yeah. So Chris has said that the Riverside project, and there's also lots of other excavations, found a lot of debris from Sarsen dressing near the monument. You mentioned that very early on, as that was going to be one part of the focus. Did you actually get round to doing any of those?
So what we've done is we analysed 2 Sarsens from 2 digs. So one from Mike Parker Pearson's dig to the north of the, I think northeast of the Stone Circle in 2008, and then the one that Tim Darville and Wainwright did in 2008 in the middle of the monument. And we've analysed all of the stones with PXRF, which took a ludicrous amount of time and doesn't show a great deal, unfortunately. It's one of those things where you're like, we've spent, because each of those analyses takes 2 minutes, and we want to do multiple ones per chip, and we spent weeks doing this. And I think the problem with these chippings is they've been sitting underground for 5,000 years. and they've weathered, and things that have got a smaller surface area weather much more extensively than big stones. And there's so much iron that's been introduced into them that many of them, it's not easy to compare with the material from Stonehenge itself. But what we are doing at the moment is, as part of this project, we got some money to, we included in the budget a little bit of money to analyse some chippings using the more high precision ICP-MS method. So we've analysed about 30 chippings, and we're in the process at the moment of looking at how they link to stone number 58. So I can't say much more about that in a minute, because we're still very much doing that, and it's very much live, and we don't quite know what the patterns of results are. But that's where we're going. There's lots to do still. But yes, potentially what we might be able to do is to be able to say, well, do those chippings come from one of these Sarsens that has a common chemistry? Does it come from stone 58? Does it come from a different stone that isn't at the monument anymore, which could be 26 or 160, or it could be one of the ones that have just disappeared completely? But we'll have to see on that. Now, we're going to try and write that up this year. So,
and sort of follow-on question from Tim, but also what I was thinking, have you had a play with any from Stonehenge that Jim Leary has dug up? We will have some as well, by the way, from in the museum, from Woodhenge and from Wainwright's excavations at Marden.
No, we haven't. I know that, Katie, you can say something about those. I know you've looked at those recently, haven't you? I say recently, pre-lockdown 2, wasn't it?
Yes, I spent most of.
We talk about things in terms of pre-lockdown, isn't it?
I spent some weeks in late September and into October working on the Marden Sarsen stone assemblage. So that's from Jim Leary's excavations, the Reading University Field School excavations at Marden Henge. So the main henge, the inner henge, and the other trenches that project put in on that site in the Vale of Pewsey. There's around 800 pieces of Sarsen stone, which range from the tiniest chips weighing less than a gram right up to small boulders. It's a real range of material, which I've been working on and doing some archaeological analysis on. Obviously, we've not been doing this kind of geochemical work on that, but it's a really interesting assemblage. I think the issue for doing the geochemical work is that most of the Marden assemblage of Sarsen stone has been burnt. The stone has been burnt. It all comes from different contexts, and so there are different reasons why that burning will have happened. But that I think is going to be a bit of a problem for the kind of geochemistry that it's been possible to do on these samples and on the Stonehenge.
Might not be, Katie, actually. Might not be, because in my parallel life in looking at silcretes in Botswana, so silcrete in Botswana was used for stone tool making. So it was earlier, middle and later Stone Age tool manufacture. And particularly, so it's in Botswana, but also very popular material in the Southern Cape in South Africa. And in South Africa, a very common approach that was used prior to knapping the stone to make the tools was to heat treat it. So they didn't burn it, but they intentionally heated it up. And what that does is it kind of hardens the cement even further. And what we've done, we've analysed we've done some experimental work where we've done experimental heat treatment to see what impact it has on the chemistry. And it doesn't affect the trace elements that we've been looking at all. It affects things like iron, it affects aluminium contents, because when you heat these things up, these Sarsens look like they're incredibly hard, but there's actually quite a bit of water in the cement.
Yes.
And what happens is they steam. So as you heat them up, the steam goes off and the stone cracks and elements get ejected out with the steam. But not the ones that we've been looking at. So I think you could possibly, even with heat treated or burnt stones, have a go. So there is potential there.
One thing, not a question, but just to highlight, is that the archaeology field groups, that's members of our society, did a fantastic amount of work in West Woods. I think Katie mentioned that very briefly. I'm just going to post on the chat a link to sort of part of that work. So if you want to follow up more, then you can see that on there. That's from Simon, which I'll email you separately, because there's sort of less questions than I think. I can see you and he having a little chat, I'm afraid.
Yeah, excellent.
He's obviously as obsessed as the rest of us are, but I think I think we'll probably call that it. So a very big thank you to you, David, for absolutely fascinating talk, and thanks for Katie to adding in particularly the Westwoods and that sort of slightly wider dimension. And I'm afraid, Katie, we're going to have to ask you not only to do your walk, but at some point give another talk about when you've the rest of your PhD study, when you finished it.
Yes.
So a huge thank you to David, and look forward to seeing many of you at future talks. So a whole bunch coming up, and we're organising a whole batch more. So very big thank you, and good night.
Yeah, have a good evening, everybody. Thanks very much. We're all looking to see if we go now, aren't we?
Finally got that. Finally got that. The link off. Yeah, fabulous. Really interesting. And you know, really interesting to do some things like Adam's grave. There's got you know, megaliths. You know, there's a megalithic chamber at the East End. You know, I know that the date's different, but you know, it's that sort of thing. You start thinking, I wonder where those came from. Because of course there are still Sarsens right up on the top of up by the top of the Alton Barnes White Horse. So you know, right on the top of the downs there. So whether those are chemically the same or not is potentially interesting as well. So there are some other bits that you know are outside those main sets of stones, but they'll be for smaller things. They're not Stonehenge size.
No, I mean, it's kind of interesting because when we set out to do this project, we weren't actually thinking that we would find the source of the Sarsens. What we were hoping to do was knock out areas. Yeah. So our sampling strategy originally was that we were going to try to knock out so that we could then focus in on particular areas that had a closer signature. But then we did the analyses and we kind of got a direct match. Thanks to Katie, I should add. For suggesting that we go to West Woods. Yeah, so
hole in one.
Yeah, well, it was kind of hole in one. Yeah, but now we've got to refine that. That's the main thing. That's not as exciting, I don't think, but it needs to be done.
Yeah. Okay, that's brilliant. So we're down to 22 people. I think we
brilliant. Good. Thanks so much.
Log off safely. That's brilliant. And I'll email you the those other questions so you've got those. And you can pick those up with Simon.
Yeah, that's great, and I can do that. I don't know how I can answer to people, but yeah. Okay.
Fantastic.
All right. Thanks so much. Then. Cheers. Have a good evening.
Right.
Yeah. Have a good evening. Bye. Bye.
Brilliant. Bye.